Hello, hello, how are you doing? Sitting here on a Friday night. It's 10 past half something. You see the clock over there. Doing the goddamn multiplier. Oh my god, it's such a big mess. So, it's a lot of stuff. So this is addition, fast addition. This is the so-called Wallace tree that I talked about earlier in one of my in real life videos. I'm talking about algorithms. So this has 17 inputs, and then you can see there's a reductions from 3 to 2. So these are so-called carry save. So why do you want to save a carry? Well, if you have a carry, when you add two numbers together, you have to ripple that carry through the whole series of bits. So say you have 64 bits, then that carry has to, in worst case, has to ripple through all of them. But here it doesn't ripple at all. You just put it out on the next here, so everything goes in parallel. However, somewhere else, when you have reduced all those 17s down to only 2 inputs, or they are called operands, but okay, operands, inputs, whatever, then you need to propagate the carry. So, but propagating them, let's say 32 bits, that will be 32 levels of propagation. Instead of 32 times 17 times. So, so yeah, so that's really great. But what the hell is a adder doing in my multiplier? Well, remember from middle school or primary school, when you add two numbers together, you start with 1 and then you sort of 1 times 0 and then all of these, and then you put the number here, and then you do the same for the next one, or the multiplier. Yeah, so then you see you get it again, and then the next time it's a 0, so then you get only zeros, but you also have to shift every time. So now there are better ways of doing this. So one way is Booth, and you probably heard of Booth. If you're working with Commodore 64, you will love Booth if you do multiplication in assembly. So, and what Booth does is it tries to reduce the amount of partial products, it's called. So depending on how many bits you look at a time, there's something called radix 4, and then you can look at 2 bits at a time with the overlaps, so you see 3 bits though. Anyway, so then you can halve the number of additions in 2. So here you have 17 inputs, so you can add 17 numbers or partial products. It's actually 16 plus 1, because we need to add 1 to its complement. And so if you have 16, and then you have 32-bit multiplication. So normally you would have had 32 numbers to add, but not in Booth. So, and then we were supposed to, or I was supposed to implement this scheme. So instead of having, let's say it's negative numbers, then let me show you. Yeah, so if you have negative numbers, you have to sign extend. That's a lot of hardware. So instead of doing that, you can say, instead of this series, as you say 1 0 instead, which means the same, I think. You may have to do some tricks though below here. So, but that's what this scheme is for. So you pad your partial product with the sign bit in this manner. So you sort of get a lot of nothing around your products. So it's easier for the tool to scrape away stuff it doesn't need. So there was something really interesting that I saw. These things here, they say that you it doesn't show on the diagram, but I know from the text. If you use this scheme, then you have to, if you have a negative number, well, then you have to make a 2's complement. Okay, so if you make a 2's complement, then you have to invert the number and plus 1. Okay, so if you plus 1, well, then you have 32 bits with a carry that must propagate, right? That's why you have the propagate. Why do you want to propagate when you have carry save adders, right? So what to do instead, just invert the number. So the dots there, that means invert. So they are inverted but plus 1. So you need a different adder than the adder you are using at all. So here you just put that sign bit under here instead. So that means if this value is negative, okay, then we have inverted it. And then if it was negative, then the sign bit is 1. So you add 1. So, and then you don't have to propagate it because it's put inside the carry save adder under here. So you see this is S1, it's put underneath there, and then this is product 2, S2, sign 2, it's put under here, so plus 1. So yeah, that's very smart. So these are things that I didn't know, so I don't know why I'm talking to to my YouTube channel about this stuff. But anyway, this is what I've been working on this week, and I can show you I had a big problem. So, and I had no idea how to fix it. So this is my multiplier. I have two inputs, A and B. Then we have the multiplication output, which is actually just the output of the summation 3 that you saw here. So that's the output over here, and then you have the carry now. So, but the carry don't care. We don't care about the carry. So sum is actually the Wallace 3 output anyway. So 0 times 0 is 0, but so I got on the sum here I got 1. So what was wrong? The thing is, in the book it says that the last operand or the last partial product you have to pad with the inverted sign. Okay, so I did that, and in the other ones you do the same, but you add a 1, but not in the last one. So why is that? So what is going on here then? Well, so we had a 1 on the sum down here, and we should see zeros. So, but why do you get 1 then? Well, these are the pad bits, and if you see here, you see 1 plus 1 is 10, or 1 0, and that goes up here, so that's a 1 carry plus 1 is 1 0 again, and so on, and that propagates down here. Actually it doesn't propagate at all because it's a carry save anyway, but we are thinking that it's propagating all the way down here, and then this last one was missing, so the one that was supposed to propagate out of this bit range was stuck in my sum. So I used maybe 4 or 5 hours on that. So for example 3 times 4 is 12, or yeah, and so on. So yeah, so I don't know how interesting that video was. Maybe I want to see the code. Maybe, just maybe. And so this is the multiplier, and that's of course the top structure. So there's a lot of work to get up to that structure. So, but what you can see is that I have a Wallace tree that I put all my partial products into, and then the Wallace tree, or the adder though, it's an adder, summates all of these individually. So then I have to make those partial products, and I have to align them in the way you see here. So yeah, so and for that I've used the process. So, and as I said, we have to observe the multiplier 3 bits at a time, and then you have the rules that we had in the book. Like here now we have if these are the bits that you are observing on the multiplier, and so if you look at these bits now, so you have pad with a 0 there now, but let's say you're looking here and you see 1 0 0 and you see 1 1 0 0, then you have to do an operation minus 2a. So how do you get minus 2a? Well, I also told you that we are working in ones complement, and that's nice because then you don't have to say invert the number and then plus 1, because if you say plus 1 then you get carry propagation. So instead we just invert the number that we want to have the minus on. So these are the operations that is possible, and then we observe the bits in a loop, and then if it's one of these patterns we then assign the operation, and also if it's a negative value, it's one's complement, we need 2 complements to make this work. So but instead of putting plus 1 here, which will generate carry propagation, put it in here instead. So as you can see on the next partial product we want add 1. So yeah, so it's a lot of details. I've been working for days and days on this, so I don't know if it makes a good video or not, but I'm sure some of you are interested. And it's quite nerdy, and I'm alone, of course, or else I wouldn't have been talking so loud in this room. So yeah, so after observing those multipliers and making the decision for what operation you want, then you have to put that operation into the partial product. And also it's important that you get that pattern right, you get them shifted right also, so that's what these are for. So if I is 0, okay, then it's from 0 to 0 n minus 1, so that's 32. So that will be 0 to 31. So if I is 1, then it's 2 to 33, right? So you get this shifting down. After you have shifted, you also need to make this padding, depending on what scheme you're using, but I use this scheme, so that's padding here. So if it's the first one, then we are going to, so you can see we have to pad with a sine, sine, inverted sine. So that's what we're doing here, sine, sine, inverted sine. And then if you're in the middle and not in the last, then you're going to add a 1 and then the inverted sign. Okay, and then in the last part of the algorithm, that's I equals 15, that will be the 16th partial product of 32 bits at multiplication, and you have to do the inverted sign. However, the book must be wrong, or I'm reading the book wrong, because if I don't add another one of the same next to it, it doesn't work. So yeah, so maybe I can show you the Wallace tree. So the Wallace tree is built up, well, you have seen it here though. So it looks like this. Has 17 inputs and then a sum and a carryout, right? The nice thing about this is that you can put in whatever bit size you want. They have 3 inputs and then 2 outputs. That's the compressors. Let's see. Yeah, there you can see. So x1 goes past, but the two other ones goes in there. So yeah. So I just written off same thing that's in the. This actually comes from a simulator, which I took a screenshot of, so it was easier for me. And then the last one, you can see the carry propagates. Let's have a look at that. Down here, tree level 1. And finally, this comes out of the last carry save adder. And it's put into the carry propagate adder. So yeah, so this task was to make the multiplier, but to make the multiplier, start with the easy building blocks, which is half adders, full adders, and then use full adders and half adders inside these carry save adder and carry propagate adder. These two are very similar. And the Valles tree is a tree of these, or a lot of these, and then one of these. So. And then all of this, or this alone, which is all of these, into these, and this one goes into that one. So yeah, so you can see the carry save adder if you want. It has 3 inputs and then 2 outputs. But what you can notice is that A and B, they are multi-bit, or the 3 inputs are multi-bits. You can see, and minus 1 down to 0, while the full adder is a single bit. So therefore you have to generate full adders, right? So if it's 32 bits, well, then you have to have 32 full adders. So yeah, maybe I can show you that. Yeah, like this. This is a ripple carry though. So the bits go down here in parallel, and the sum is updated in parallel. However, the carry has to propagate through, so we have to wait for that also. There you can see the 3 to 2 count. It's a counter actually. It counts the number of bits coming in. So yeah. And it's also difficult to reading. It's not actually bits. It's operands. That means it can have 8 bits or 32 bits on each of them. So, but it counts the number of bits inside here and puts it out there. So there you can see a carry save adder. So instead of running all the propagation like here, this is a propagation adder. And these are full adders, by the way. Full adders, that means that they can take a carry input like this, then you can summate. So, but carry save, it's instead of sending the carry to the next one, it sends it down the tree. So then you don't lose any time, because the time it takes for the carry to propagate, well, it doesn't propagate, actually it just falls down on the next weight. So yeah, so but however, when you come down here, you have to propagate it also. But if you have many operands to summate, then you have to do it. So then you save a lot of time by propagating only once. So yeah, here you can see Wallace tree. With full adders, it looks a bit more complicated than when you're using or displaying it like this instead. So yeah, so he was a smart guy. This was in 1964. Yeah. Anyway.